I think it's time to get started. I don't really hear the bell. As we said, we'll start chapter 2 today. Okay. And chapter 2 is talking about analysis of a linear time invariant system and also called LTI system. This is quite an important chapter. This will be the basis of almost everything we do later on the course. Okay, and so we start with discrete time because it's easier. So today we'll talk about discrete time LTI system and teach you this important concept of convolution. Okay, and let's get started. And as a review, so last time we talked about system properties. And there are those two properties that we care mostly about, that's linear and time invariant, because they persist in a lot of physical systems, for example, in the electrical circuits, and also if you have both properties, it makes the analysis of our system a lot easier. Okay, so as a reminder, so linear is this property where you have two different input-output pairs, so x1 input mapped to y1 output, x2 output. So any two input-output pair, x1 mapped to y1 and some x2 mapped to y2, then the linear combination of input will get mapped to the linear combination of output. So for every alpha x1 plus beta x2 will get up to mapped to alpha y1 plus beta y2. Okay, so this is linearity. And then the second property is time invariant, and this is more subtle property to write down. It means that for any input-output pair, so any x mapped to y, then if you may give a time shift to x, so x of n minus n0 as input, then the output will be the corresponding time shift in y. So the output will be y of n minus n0. Okay. And as we say, so linear time invariant system, and we'll abbreviate this as LTI. So an LTI system is just a system that's both linear and time invariant. Okay, so it satisfies this property and this property. Okay, so this should be okay. So this is LTI system, and now we see. Okay, so this is LTI system, and now we see how we analyze an LTI system. So the idea of analyzing a LTI system, at least for now, is we write the input signal as a linear combination of unit impulses. So that's why we talk about unit impulses in chapter 1. Okay? And once again, as a reminder, unit impulse is a very simple function that's just you have a spike somewhere. So you have a delta of n equal to 1, when n equal to 0, and it's 0 everywhere. It's very simple. It gives you it's just 1 and n equal to 0, and you can move this spike around by giving a time shift to this unit impulse. Okay, and so unit impulse is very nice because it has this sampling property, and if you use the sampling property a little. It has this sampling property such that you have your function times your unit impulse, then become the function value at 0 times the unit impulse. This is a sampling property. So x of n times delta of n equal to x of 0 times delta of n, etc. And okay, I guess we don't necessarily need to use that. But anyway, so unit impulse is very simple, and so that we can write any signal as the sum of unit impulses. So for example, we have x of n, and we can think it as this is a discrete signal, so we can think it is a sum of different spikes. And so it's x of 0 times delta of n, so this is a spike at 0, plus say x of minus 2 times delta of n plus 2. Okay, so this will be this spike at x equal to minus 2, and also this spike at 1 is equal to x of 1 times delta of minus 1. So sorry about talking about sampling property. We don't actually need to use sampling property here. Sampling property here, we just need to have the property that Well, unit impulse is very simple. So unit impulse times some height can represent each spike in this signal. Okay, so we have a spike at 0, spike at -2, spike at 1, spike at -1, etc., and spike at 2. Just have the delta function times the corresponding function value at that point. Okay, and so what we are saying is we sum all those things together, then we should get back to our x of n. Right, this is just very straightforward. So you have the function value at 0, at -2, -1, +1, +2, etc. So you're summing over all the different function value at different points, you get back to the original function or original signal. Okay, and yeah, so that's the idea. So any signal, any discrete signal can be written as this linear combination of impulses. Okay, so x of n will be, so you sum from -infinity, k from -infinity to +infinity, and your function value at k, so x of k, times delta of n minus k. Okay, so this is the idea of this is how we use basically how we use linearity. So first we express our signal as a linear combination of those unit impulse signals. Okay, any questions so far? I think this is the basis of all the analysis we will do today. Okay, yeah. So the idea is your system is linear. Okay, so it's a bit confusing. Your system is linear, but we haven't talked about system anymore. We are just talking about any signal. So this will x of n will basically be our input signal. So we put our input signal as a linear combination of those impulses. Okay, and then yeah, and we keep talking about linear. Okay, so now we use linearity. So our system is linear. So if we write our input signal as a linear combination, then by linearity of the system, so we know we map x to y, then this y will be a linear combination, the same linear combination of the corresponding output signal to those basic input signals, or those impulses, they should be mapped to something, and we just write it as h of k. Okay. So yeah, so here is just linearity. So x is a linear combination of delta, then input x is a linear combination of those delta function, then the output should be the same linear combination, so we have the sum over sin k and the sin x of k, and then the corresponding output signals. Okay, so the h sub k of n is output correspond to delta of n minus k, so we write it here. So x as input, output to y, and delta of n minus k, output to h sub k of n. Okay, and here, yeah, so this is sub k just means that it corresponds to different tangent n minus k here. Okay, and for now, this h sub k of n is an arbitrary signal. This is well, this is not quite arbitrary. This is but this is a signal that the system will map delta of n minus k into. Okay, so different system can have different h of k. Okay, and here is some example that are just showing some picture. So we have some input x as a linear combination of delta of n minus k. Then output is y. Output y is a linear combination of h sub k of n. Okay, and so this is a real picture. So maybe you have three different h sub k. So we have an input signal that's only non-zero on -1, 0, and 1, and then the output signal should also be a linear combination between k equal to -1, 0, and 1, because x of k is non-zero only when k equal to -1, 0, and 1. Okay, and then maybe the system just have this pretty arbitrary h sub k. So h sub -1, h sub 0, and h sub 1 here. Okay, so yeah, the different system can have different h sub k, and then we can calculate the output from the input and those h sub k. So we just have the input at -1 times the h sub excuse me, so input at -1 times h sub -1 equal to this, and the input at 0. So input at 0 times h sub 0 equal to this, and input at 1 times h sub 1 equal to this. So add those three signals together, you have the output signal y of n. Okay, that's the idea. And those three outputs, those three hk, h sub k also correspond to three different parts of the input. So it corresponds to x minus 1 times delta of n plus 1, and this corresponds to x of 0 times delta of n, and this corresponds to x of 1 delta of n minus 1. So you split your input to those three parts, and they have those three corresponding output, and then you add those three back together, you get the output. Okay, and so output is the sum of the responses to different time steps. Okay, that's linearity. Okay. And so linearity gives us this nice input and output relationship, and basically we find out that if we want to find the output to any signal, we just need to look at this h sub k, and time invariant gives us even better property. So time invariant tells us a nice relationship between different h sub k. So far on this slide we only use that. The system is linear, and now if the system is also time invariant, and then we have this, we can write down this time invariant block for our delta function. Okay, so we know each delta function, delta of n will get mapped to delta of n will get mapped to h sub 0 of n. Okay, so this is by definition, because we say delta of n minus k get mapped to h sub k of n. So k equals 0, then we have h sub 0 here. Okay, and then we time shift our delta function to delta of n minus k, and we say by definition we say this thing mapped to h sub k of n, and but by time invariant we know that this thing should also equal to this h sub k should also equal to the time shift of h sub 0 of n. Okay. So the time shift of h sub 0 of n is equal to h sub 0 n minus k. And by time invariance, so when we talk about time invariance, we say this thing should equal to this thing. So time shift, so you map to output first, then do time shift should equal to you do time shift first, then map to output. So this h sub k of n should equal to h sub 0 of n minus k, and this should be true for every k. Okay. And this should be true for every k. Then we find out that basically we know every h sub k. So every h sub k is the same, basically the same as the h sub 0, but just apply with the time shift. Okay. So if the system is all time invariant, then we see that every h sub k is basically the same. This is the time shift of h sub 0. And to make the notation a little easier, now since we only have one h, we call h sub 0 as h, and then so h sub 0 is h, so we have h sub k of n is just h of n minus k, and we put that inside this. We see that for the linear time invariant system, we have y of n equal to summation k from minus infinity to plus infinity, s of k times h of n minus k, and so this is the most important equation we have in this chapter, and very important equations throughout the whole course. Okay, so this is the equation you should memorize, and this is the equation is so important. We also have a name for it. So the equation is called the convolution sum. Okay, and we can even give it a special symbol for it. Okay, so this summation k from minus infinity to plus infinity, x of k, h of minus k, we call it a convolution sum. We call it a convolution sum, and we think it as a convolution between two different signals, or two different signals. So this is x of n signal and h of n signal. Okay, so we use this notation, x of n and this star h of n is we write this. Then this means this this equation, summation k from minus infinity to plus infinity, x of k, h of n minus k. Okay. And yeah, here is just some notation, but this is a very important equation that you should definitely memorize it. And we'll let you stare at it for a few seconds and think about whether the derivation makes sense. Okay. Before we talk about the consequences of this equation. Okay. Everyone okay with the derivation of this convolution? Okay. Yeah. So we derive that for an LTI system. Y of n equal to summation k. This is a convolution between x of n and h of n, and x convoluted with h is equal to summation k, s of k, h of n minus k. This is very important. Okay. And I guess another important thing I should say here, although it's written here, it's written here, is that now this h function is very important. Now this h function is called the unit impulse response, and I think the name here is very important. The name here is very intuitive because h is the response to unit impulse. This is a system response to delta of n. Okay. So, this is the definition of a unit impulse response, and this definition is so simple. We even keep this definition for non-LTI system. Although for non-LTI system, the unit impulse response is not so important. Okay, so unit impulse response of a system is just whatever output correspond to the input delta of n, at least for discrete-time system. Okay, and I guess. The important concept here is that, first is that we see that the output of a TI system can be expressed as this convolution operation, which is this weird summation. And but a very important consequence here is that we see that the whole system is characterized by this unit impulse response H. Because as we say, we characterize the system as how you calculate the output signal from the input signal, and you see that how the output signal is calculated. Well, the output signal only depends on this input signal x, obviously, and the unit impulse response h. So if you know h, then you know the LTI system. Totally know the LTI system because you can calculate every input-output pair. The output is totally determined by the input and h. Okay, and so I guess this is something very nice, but also a little confusing because h is a signal, and the signal characterizes the system. Okay, in chapter 1, I told you that system and signal are different things. System is a thing. A system is basically a function or mapping that map one signal to another signal. Okay, but here we see that the system can be described by a signal. Okay, and so that's a bit confusing. So I guess you just that's a bit confusing, but do not miss. But please do not mix things too much in your head. So although this h will totally determine the system. So this is a system of arrow here. This LTI system x to y, and you still remember we have the system is a system. A system is something that maps a signal to another signal, and h is just a signal that will kind of nicely characterize the behavior of the whole system. Okay, and I guess a bit of spoiler, since h is so nice, h characterizes every character of the whole system, so the system property of a LTI system can be also calculated from the h. So like causality, time invariance, etc. Those property can be also determined by looking at the unit impulse response h here. Okay, so so this h is very nice. Okay, and that's some source of confusion. So Okay, but for now, we know H is very nice, and for now we'll let you get more more intuition about this convolution operation. Okay, and any questions so far? If not, and yeah. And then let's get our hands dirty and do some actual calculation with convolution. And I think it's nice to build an intuition about how this convolution operation look like. I guess one thing, a little criticized about and the confusing part of this notation here. So the notation here we write x of n convoluted with h of n, but but it's important to remember the different variable here. Okay, so n here is the time variable. So our system, our signal has this independent variable being this is n here, and so input signal has this independent variable n, and output signal has this independent variable n. And here those x of n convoluted with h of n. Personally, I think those two n are kind of don't have much meaning here. It just means the independent variable here for everything is n. And so what I want to say is you need to remember that the summation here is with k. Okay, so we are summing over another dummy variable k here. And yeah, so here we are summing over k, different k. So we have x of k, h of n minus k. And and how this equation depends on n is only here. So you have h of n minus k, and this n is this y of n here. Okay, for those two n here are kind of don't correspond to anything. It's just a notation here. Okay, and yeah, we'll see soon that the variable n and k is a bit confusing. But anyway, so let's get some intuition about convolution. And so we have you can have two different ways to think about convolution. Okay, kind of correspond to whether you want to write your signal in terms of n or signal in terms of k. Okay, so first is I think the most straightforward way. So we have y of n equal to x of n convoluted with h of n, and it's this summation sk h of n minus k, right? So you just have different k as a different signal of n right down here. So you have x of 0, h of n minus 0, and h of 1, x of 1, h of n minus 1, etc. adding together. And so here we have an example. So our h of n equal to this signal that's 1 at 0, 1, 2. And our x of n is also very simple. It's 0.5 at n equal to 0, and 2 at n equal to 1. Okay, and then we can write down this convolution as our intuition of a linear combination between response to this spike and the response to this spike, right? So we can have when k equal to 0, then we have a response to this spike. So that's 0.5 times our h of n. Okay, and so 0.5 times h of n, and that's 0.5 on 0, 1, 2. And then we also have okay, and then we also have the response to the next time step. So response to this time spike, this spike, and that will be response to this spike will be 2 times this thing and shifted by 1 step. So 2 times h of n minus 1. So it's this 2, 2, 2 between 1, 2, 3. Okay, and yeah, so this is a very straightforward interpretation. You have a linear combination of the response to different time step, and you see the response to each time step have the same shape because it's just a time shift of this this response at time equal to 0 spike. So it's time shifted and have different height correspond to you have a different input strength at different time step. So you add those two together, you get the output, and so it's 0.5, 2.5, 2.5 to signal. Okay, so this is I think the straightforward interpretation of a convolution. Okay, And but you can also calculate convolution in I guess a different way, but really the mathematics is kind of the same. But you can visualize a little differently. Is you fix an n and think about how what the summation over k will be like. Okay, and so to view this, really we want to think about h of n minus k as a function of k. Okay, so here we view this h of n minus k as a function of n, and now we think about h of n minus k as a function of k, and we want to multiply this function of k with this function of k that's s of k, and summing over ok. But let's first write down what's this. How should you visualize h of n minus k? So first we write down h of k. So h of k as a function of k is really just h of n, but you change the name n to k. Okay. So this is h of k as a function of k is 1 1 1 on 0 1 2. Okay. And now this is why we want to talk about transformation of independent variable on chapter 1. Now we do two transform on independent variable to change this to h of n minus k. So I think the most intuitive way is you first change to h of minus k. Okay, so h of minus k, so you do a time inversion on this k, and so you should flip everything around 0. Okay, and so you still have 1 1 1, but instead of going from 0 1 2, you go to 0 minus 1 minus 2. Okay. So this is h of minus k, and to go from h of minus k to h of minus k to h of n minus k, this is really h of minus k minus n. Okay, so you do a time shift on k, and you do a time shift of minus n, and as we say in chapter 1, this is delaying your signal. So you will drag your whole signal to right by n, okay, because you change k to k minus n. Okay, and so your signal is still this 1 1 1, but it's from 0 minus 1 minus 2 to n minus 1 minus n, and n minus 1 and n minus 2, because you drag the whole signal to the right by n. Okay, so yeah, so this is your h of n minus k as a function of k. You flip things around and drag to the right by n. Okay. And then, yeah, now we can think about how this summation look like for different n, because we have write down how h of n minus k look like for different n. Okay, so so this summation has two different parts. So s of k, kind of like just h of k. S of k is just a x of n. We change the name of variable from n to k, so it look like exactly like s of n. Just the variable name here is k, so it's 0.5 and 2. Okay, and h of n minus k will be this signal, but its location will shift to left and right, depend on how you n. And from the derivation here, we know when n is smaller, our signal is to the left side. Okay. So when n is less than 1, then we see our signal is n minus 1 and minus 2. Somewhere on negative. Okay, now we think about this summation here. So summing over different k and s of k times h of n minus k, and so you see both of those two signals has finite support, and they don't overlap when n is less than 0. So you multiply them together on each k, you see that whenever you multiply together, it's something times 0, something times 0. So when you multiply them together, it's 0, and you sum over a whole bunch of zeros, it should just be 0. So when n is less than 0, the convolution is always should be 0. Okay, so you keep increasing n, and I would like to visualize this as you drag the h of n minus k to the right one by one, and until one step by step, and until you have overlap between h of n minus k and k. And first time that happens is when n equals to 0. So h of 0 minus k will be the signal. Okay, so the signal from minus 2, minus 1, 0. And so now, now you have overlap, and you do this multiplication of s of k, h of n minus k on each k. and you see they only have overlap on this k equal k equal to 0. So you have k equal to 0 is x of 0 times h of 0 equal to 0.5, and so this equal to 0.5 when n equal to 0, and that means y of 0 equal to 0.5. And you keep drag this to the right, and when n equal to 1, you have 2 overlap here. So you have 0.5 times 1 here and 2 times 1 here, and so the result is 2.5. And to the right even more, then you have this 0.5 times 1 plus 2 times 1, and that's 2.5. And to the right even more, then you have a fewer overlap now. The overlap is only 2 times 1, and you equal to 2. And you to the right even more, when n is greater or equal to 3, you once again you see this h of n minus k, and s of k has no overlap. And so s of k times h of n minus k will just be 0, and then you summing over everything is still 0. Okay. And yeah, so that's another way to see this 0.5, 2.5, 2.5, 2.0 signal. Okay, and yeah, so it's this signal 0.5, 2.5, 2.5, 2. Okay, any question? And I guess the first, although the first way seems more intuitive, when you want to calculate the closed form expression for the convolution result, what you actually do is the second way. Okay. And yeah, there will be a lot of homework problem and even exam problem asking you to calculate the convolution of 2 different signals. And this is basically the thing you will do. You will think about what the h of n minus k, and yeah, a lot of time you need to think about the overlap between h of n minus k and s of k, and you need to do a lot of case analysis because they usually have different boundaries, and you need to think about how different boundaries overlap, and for different region you will have a different expression. Okay, we'll soon see more example of this. Okay, yeah, so larger example, so example of a field infinity is this x of n equal to alpha to the n u of n, and here we assume alpha is less than 1, so your x of n is this decaying function. We plot with alpha equals alpha of n. Sorry, we plot with alpha to the alpha as something less than 1. But obviously, when you calculate the this should be good. Yeah, so alpha is something less than 1, so we have this decaying signal, and h of n now is this unit step function we talked before. So it's 1, 1, 1, 1, 1 starting from n equal to 0. Okay, so this is a very strong response. You hit the system with one spike at n equal to 0, and they just keep repeating until infinity. Okay. And we'll repeat the procedure we had before. So we want to see what's h of n minus k for different n. Then we flip this h of n or h of k left to right, and drag this from n to minus infinity to plus infinity, and look for when these two things has overlap. Okay. And so h of minus k will be this thing, so it's this step function extending to unit step function extending to minus infinity, and if n equal to minus 1, then this thing will push to minus 1, so this step will start at minus 1, and this if n equal to plus 1, then this thing will drag to plus 1, and if n greater than 0, then the step look like this, and n less than 0, then this step will look like this. Okay, well, okay with the change of independent variable. If not, okay, and yeah, so now we know how different h of n minus k look like. Then now we think about what's the overlap between h of n minus k and x of k. And once again, when n is less than 0, then you see that h of n minus k and x of k just have no overlap, because this thing is 0 when n is greater or equal to 0, and this thing is 0 when n is less than 0. So they have no overlap. So you multiply together, it's just 0 function. And this sum over 0 function is 0. Okay, and when you do have overlap, then then the overlap is from okay, and when you have when n is greater or equal to 0, then your two things have overlap. So you have the summation k from minus infinity to infinity s of k, h of n minus k, and you see the summation is you sum over. So in this case, when you do have overlap, you see that well it's all 1 here. So you are based on your s of k from 0 to n. Okay, because the state function says that from 0 to n you multiply 1, and then when greater or equal to when k is greater to n, then you are multiplying 0. So you have this function times this function is just this function from 0 to n. Okay, and yeah, so when n is greater or equal to 0, you are summing over k from 0 to n, and you have this x of n, so that's alpha to the k. And so summing over k from 0 to n alpha to the k is summing over geometric series, and you can write down yeah, and this is summing over geometric series, and sum over geometric series you can really look up the formula is this thing. So 1 minus alpha dividing 1 minus alpha to the n plus 1. Okay, and when you plot it, and so this is when n is greater than or equal to 0, and when n is less than 0, we know it's 0, and to have these two conditions writing in a single equation, we just write u of n here. Okay, so we know y of n is 0 when n is less than 0, so just like this. And when n is greater or equal to 0, it's this equation. And if you plot this, then you look at this. So it's an exponentially saturating function. Okay, so it's 1 minus, when n goes to infinity, you just have 1 over 1 minus alpha, and it's approaching this 1 over 1 minus alpha with well, the difference is exponentially decaying. This is alpha to the minus 1. Okay, any question with this example? So yeah, so once again we see how you have overlap, and you when you think about overlap between s of k and h of n minus k, you have a different region, and yeah, so we basically deal with different regions separately, and and yeah, and we can also write down algebraic equation for different regions. Okay, and finally we see a very complicated example. Okay, so yeah, this example is very complicated because both x of n and h of n has two different boundaries. Okay, so x of n look like this signal, so it's 1 between 0 and 4. So you have a left boundary on 0 and a right boundary on 4. And h of n equals to alpha to n, and they also have two boundaries on 0 and 6. Okay, and yeah, and then we think about the convolution of those two functions. And once again, we need to think about h of n minus k, and I think hopefully by now we are very familiar with this. So first we flip this around at 0, and then we shift left and right depending on what's n. Okay, and so you flip this around, so it becomes an exponential function like this, and then you have a negative n, then you will push the signal to the left. Okay, and so s of k just like look like s of n as before, and then you need to think about h of n minus k. So, and just like before, we see that h of n minus k has no overlap to x of k when n is less than 0. Okay, so when n is less than 0, h of n minus k and x of k is no overlap, so y of n is just 0. And then we keep increasing n, then you will hit s of k when n is 0, at first, and when n is between 0 and 4, we see we have this partial overlap between SOK and HO minus K. Okay, so this is case 2 or interval 2. So n is between 0 and 4, and we have this partial overlap, and the overlap will be this is summation from K from 0 to n, and the value here we don't go to too much detail, but let's see. I guess we have a bit of time. Yeah. So summation from summation. So you see the non-zero K is from 0 to n, and then the value here it should be h of n minus K, and because h of n was alpha to the n. So h of n minus k was alpha to the n minus k. So those three values are alpha to n minus k. So we sum, and then alpha to the n minus k times SOK is just 1. Okay. So alpha to the n minus k is summing from 0 to n. And then once again, you can apply geometric series formula to get this is this 1 minus alpha to the n minus 1. So 1 minus alpha to the n minus 1 over 1 minus alpha. Okay, and I guess important sanity trick when you do these examples that the result here should have no k. Okay, because the calculation is very complicated. So sometimes you will forget what you are summing over, etc. And yeah, so it's important to remember that k is a dummy variable you are summing over, and after you do the summation, your answer should have no k. Your answer should be a function of n, not a function of k. Yeah. So yeah, and as we see, the result here is has no k. And okay, so back to our interval discussion. So this is the second interval. We have partial overlap, and if you keep dragging the signal to the I guess keep drag the response to the right, then when n is greater or equal to 4, we have that we have 4 overlap between h1 minus k and SOK. And so this is when this boundary is to the right of this boundary, so n is greater to 4. And also we want this boundary to be the left of this boundary, so we have 4 overlap. So, and this boundary will be n minus 6, and so we want n minus 6 to be less equal to 0, so that's n less equal to 6. Okay. And when in this case, we are summing from 0 to 4. Okay, so we are summing from summing k from 0 to 4, and once again, the value here is h of n minus k, so that's just alpha to the n minus k. And then once again you do geometric series formula, you get this result. Okay. And yeah, and this result, as before, is a function of n, it's not a function of k. And the next one, we drag the signal to the right even more. Then you see that once again we have partial overlap because the left boundary of this response signal is between this x signal. Okay. And so we will summing from n minus 6 to 4. Okay? And so we sum k from n minus 6 to 4 alpha to n minus k, and we get this result. And this is also important to determine the value of the interval. So this is when n is greater to 6, and also you want n minus 6 to be less than 4, so n is less than 10. And finally, when n is greater than 10, you have no overlap at all, and once again the signal is 0. And here is the here is the plot of the whole signal. So you can feel that your overlap is increasing and kind of peak here, and the overlap decreasing and go back to 0. Okay, any questions so far? And here we skip something, and I guess if you want, although I think this is a bit dangerous, and you can also do this thing with fully algebraic way. And so if I guess if you are really confident in your algebra, you can write say your h of n as a fully algebraic way to describe those boundaries by using unit state function. So you say you can have your h of n equal to alpha to n, so this part, and you set this boundary from 0 to 6 by just saying it's a unit state function from 0 minus a unit state function from 7. Okay, so this will be a function that's from 0 to 6. Okay, and yeah, and then you also write so you can write your h of n like this difference, this exponential signal times the difference between unit step function, and you can also write your input x as the difference between unit step function, and do convolution there fully algebraically, but yeah, you can do that, but I think you still need to do case analysis because then you have a whole bunch of overlap between unit step functions, and yeah, so in the end you will still get cases, and yeah, this is just another way to do this, but I think it's a bit more straightforward to draw the function here and see the overlap. Yeah. Okay. And here is the most overlapped example, and I think we have one more example here, and this is a bit weird example. So this is an example where our signal does start from negative infinity and stop somewhere, and our response is still the same. So there is response is something we've seen before. The response is a unit step function. Okay, so response is something start from 0 to infinity, and you flip it around, so you extend to negative infinity instead, and then you drag it left or right with this n, and it's something that stop at n. Okay, and yeah, so because we've already seen this h of n, so we just draw h of n minus k here. So it's something that start from negative infinity being 1, 1, 1, and stop at k equal to n. Okay, and x of k is this weird function that's exponential growing, but from negative infinity, so it's like exponential decaying to k to negative infinity. Okay, so x of n is this thing. And now we think about how those two things look like, and this thing I think only has two intervals. So first interval is when n is less than okay, so we do this a bit funny. So we start with a larger interval. So the first interval, when we have n greater or equal to 0, then for everything, so whenever n is greater or equal to 0, you see x of k has four overlap to h of n minus k. And so this thing is just summing k from minus infinity to 0, and this x of k just equal to 2 to the k, and so you do this summation of geometric series is 2. And and then when n is less than 0, we have this partial overlap between h of n minus k and x of k, and we see its overlap is from k to minus infinity to k equal to n, and just summing over this 2 to the k from k to minus infinity to n, and in the end you should get this 2 to the n plus 1 result. And remember n is negative, so when n is more negative, this number is smaller, and so this is like an exponentially growing function from almost 0. And yeah, so this is a full function, so you have an exponential growing here, and you pick it when it's greater than 0, it's just keeping 2, 2, 2, 2, 2. Okay, and yeah, I think we are exactly on time, and that's all I want to talk about today. That's the convolution of discrete-time LTI system. Okay, yeah. We have no question. Then next time we'll go to continuous time LTI system, and we'll also have convolution. Okay, so yeah, see you next Tuesday. Oh, sorry, next Monday. Yeah, and you can put your homework here, and the TA will collect them. Okay, thank you.